Good afternoon and welcome to the Open Systems Media webcast, Efficient Ways to RF Test Your IoT Device, sponsored by Anritsu. My name is Rich Nass and I am the Executive Vice President of Open Systems Media. I lead the embedded IoT teams for embedded computing design. But more importantly, I will be your moderator for this webcast. On this webcast, you'll be hearing from Brian Davis, a Market Development Manager for Anritsu Wireless. Brian has over 20 years of experience in the wireless communications industry, holding various positions in engineering and management at Motorola, Ericsson, Qualcomm, Zyre Wireless, and Broadcom. That's like the who's who of wireless. Throughout his career, he's worked in both hardware and software development, and in his current role, he specializes in mobile applications. Brian holds a BS degree in computer engineering from Michigan State University and an MBA from Colorado State University. Before I bring Brian out, let me talk a little bit about the webcast today and what you can expect to learn. IoT is often described as the Wild West of the RF world with all the various standards and different implementations of those standards. From a testing perspective, it gets even wilder, as you can imagine, with all the different implementations of people going in every different direction in different geographies. So this webinar will focus on conducting RF measurements for an IoT device using network simulators, and that includes 5G, LTE, NB-IoT, Cat-M, wireless LAN, V2X, Bluetooth, and Zigbee, and pretty much any other acronym you could think of that has to do with this space. It's very inclusive, and I'm sure you'll get a lot out of it. Let me go over some of the housekeeping stuff next. The entire presentation will take somewhere in the neighborhood of 45 minutes, give or take a few, and that'll leave us some time to answer your questions. And we will get to as many as time permits. You'll find on the console window, there's an area where you can enter your questions in real time. And as I said, we'll address as many as we can when Brian is finished. We tend to answer questions in chronological order. So I suggest as soon as you think of a question, you put it into the console. Don't wait until Brian is done, because then we might not get to it. If we do not have time to answer your question before the time runs out at the top of the hour, someone will get back to you after the webcast is over with an answer. It might be by email, by phone, and obviously not part of the webcast, but every question will be answered. If you have a question pertaining to the operation of the webcast, like if the slides are not working right or the audio doesn't sound right, put that question into the box, and one of our technical folks will respond with a fix for you. There's a maximize button on there that lets you see the slides in a larger window. And this webcast will be available in archived version when we're done. So if you miss something, you want to go back and review, you want to send it to a colleague, it's there for you. We also have one poll question about a third of the way through that we'd love to hear your answer to. It helps Brian figure out a little bit what the audience is working on, and he can spend more time or less time on particular areas. So please answer that poll question when we get there. I think that's it. Let's bring Brian out to start the presentation. Take it away, Brian.
Okay, thanks, Rich. Good morning, good afternoon, or good evening, wherever you are in the world. I know we have a lot of people tuning in from overseas, so thanks for joining us this morning, and look forward to educating you about efficient ways to RF test your IoT device. So here's a little topic that I put together, a list that we'll talk about. As Rich said, there is a lot of things going on in IoT. So I wanted to just educate you a few minutes on the key wireless technologies, the ones that seem to be the predominant ones that are more open standard as well. There's some additional ones that are more closed standard that we dabble in a little bit here and there, but for the most part, it's the open standard ones. Then I'll get into measurement instrumentation. This is where I've got a lot of great screenshots. I really want to show you the GUIs that Anritsu has developed over the last few years. You know, they're very intuitive. We get a lot of great feedback from customers. They're award-winning GUIs. Really help you take some great measurements. I'll get into the measurements showing some of the key ones, kind of going from the simpler ones and then building on top of those so you get up into the larger type measurements with more key aspects, more greater visibility into what's going on. So starting off with just basic power measurements, then we'll get into frequency, modulation, phase and amplitude measurements, and then receiver sensitivity and error rate measurements. Then we'll build on top of that and get into simultaneous technology testing, where you're using multiple radio technologies at the same time, and then how coexistence testing, where you have multiple technologies and you need to see how they affect each other as well. And then even building on top of that, we'll get into a little bit of carrier aggregation and MIMO. Anritsu's got some really great methods to test both of those seamlessly. GUI does a great job of testing these and giving you feedback. And then I'll talk a little bit about signaling and non-signaling measurements and what that means. There's a lot of trade-offs and benefits to both of those. Then some manual and automated testing programs that we have available. I've got some great screenshots on those. And then finally, I'll get into the Anritsu equipment and give you some greater detail on how they can help you test out your device. So getting started with the standards, for cellular side, it's predominantly 3GPP. And 3GPP is a standard, an organization that derived out of GSM days in the 80s. They've kept the 3GPP name just so they don't keep having to evolve it when you get 4G, 5G, etc. So it's a little misleading that it's called 3GPP, but they're the ones that are responsible for the specifications of the technology. They revise the specifications about every 4 years. There's incremental evolutionary steps inside of those 4 years. But for the most part, every 4 years there'll be a big jump, and these are some of the big jumps that I've got here, and I'll get to in a second. But they're not responsible except for acceptance or conformance testing. That's a completely different entity called GCF, PTCRB, and then you've got the carriers with their own conformance testing as well. So going along the middle there, LTE 3GPP release 8 and 9 were the first LTE releases, and those provided a path for the operators to migrate from GSM or UMTS, WCDMA networks, and CDMA2000 networks. They really paved the way for the underlying LTE PHY layer, which were the biggest changes to get you the faster throughput. Then they went to an LTE Advanced in Release 10 of March 2011, and then some of those networks were migrated, which were initially launched in 2009 with LTE. Then they had the LTE Advanced Pro in Release 13 and 14, and those incorporated new technologies which kind of paved the way for LTE or 5G, things such like 256 QAM, higher modulations, massive MIMO, unlicensed LTE, and then they started to get into the IoT. 5G, now that's all the latest buzz right now, that's expanded into greater efficiency, ultra-reliable, low latency, wider bandwidths, and then of course the millimeter wave aspect to it. And I'll talk about that for a little bit. As those technologies advanced, they added narrowband, smaller, more nimble communications methods for efficient battery consumptions, and those are Cat-M, LTE Cat-M there. It has voice, mobility. Again, it's narrowband, low power, low data rate, and that came out in Release 13, and then narrowband IoT came out in Release 13 as well. And that works in a lot of the guard bands for LTE. But the core 3GPP specifications for RF is in Release 34, 36, and 38 as the technologies migrate. On the short range side, the predominant communications we've got is, of course, Wi-Fi and Bluetooth. Everyone lives and breathes by Wi-Fi and Bluetooth. And then you've got some smaller standards there, Zigbee and Z-Wave, which are meant for small bursty communications, mesh network kind of things. small amounts of data. There's some use cases in industrial and retail for Zigbee and Z-Wave. But for the most part, they're very small amounts of communication. So when you start having to test all this stuff, you really need some kind of interface that can show all of these key test items. And these are shared across all of those different standards and technologies that I already mentioned. You know, you've always got to test transmit power, bandwidth, spectrum emission, adjacent channel, frequency error, EVM. You know, you always want to look at your constellation plots and then see how your sensitivity performs. Those are really key aspects, and you want to be able to test those consistently, reliably, and very quickly. Now, when we get to 5G, the test equipment industries had to evolve for the millimeter wave side, right? Because you can't bypass antennas and do coupled testing like you could for sub-6 gigahertz. The antenna's integrated with the baseband, with the RF front end and all that. So you really need to use a lot of the technologies and ways to test that the antenna industry has been doing for a number of years for performance verification. So total radiated power, peak beam search, those kinds of methods. Those are relatively new for a lot of the core baseband modem device makers that have traditionally been using sub-6 methods. And then finally, automation test software. It's getting to be there's so many bands, so many combinations of bands and channels. Carrier aggregation is pretty much required for a lot of devices that need high bandwidth, high throughput. And to try and do all that manually would just be impossible. So you really need some good automation software that's reliable too. It gives you clear and concise results, different result formats. I'll get into some of that as well, but here's kind of the overview of what you really need to be successful in testing RF for IoT devices. So this is just a screenshot of our main cellular RF application. You can see it's got a nice black background for easy visibility. We work with our development team quite a bit, getting them a lot of customer feedback on what customers want. Make things more easy to use. Touch screen has been a fantastic feature to put into test equipment. But a lot of test equipment, it used to be in different physical boxes. Now it's all kind of being combined to what's being called a call box. So you're able to take multiple measurements in a single physical piece of equipment. But going along the top here, you've got a nice numerical values. They'll give you an overview of multiple measurements simultaneously. You can get into detail if you want more detail on specific measurements. And then over on the right there, we've got several different kinds of graphs, and those graphs can actually be broken out into additional detailed graphs as well. And with the Anritsu equipment, I like to say that there's usually 2, sometimes 3 ways to see results in the same manner, or in different manners on the equipment. You can get numerical results, graphical results in different ways. It's really up to how the user wants to do it. And it's very flexible to be able to go in and change around what you want to view very quickly, touch screen or using a mouse. So some of the features of the Anritsu GUI is that we've got a lot of ways that you can edit parameters, change parameters, look for information. So on the top left there, you've got the ability to do searches. So you touch the search icon there, the little magnifying glass. It pops up a keyboard. You can start typing in what you're searching for, and it'll bring up all those parameters in the search. You can also bookmark parameters that you've used quite often, so you're not having to go around and search for the parameters. They're on the tabs on the left. You can also zoom in on any of the frames there on the right, you can zoom in and get additional detail. And some of these measurements are available in three-dimensional as well as 2D. So you can change parameters from default, and anytime the parameters change, they'll change color from default. So you'll go from a blue to a yellow. So that's nice if anybody comes along and they need to figure out what the previous guy was doing, or you forgot what you had changed. You can go back and see what you've changed based off of the color or a search of last parameters changed. There's the bookmark there on the right, so a little star icon, and then the magnifying glass for the parameter searches below. Here's just the example in more detail of the parameter searches. So you can get the keyboard pop up. It'll give you a green color there to show all the parameters that start with CH. There's an automatic help. So if there's any parameter that you want more detail of what does this do? What does this change? You'll get a little frame on the top right there where it'll explain what the parameter is. And then if you expand down on that, it'll give you Skippy command information. So this has been very handy when some of our customers have been developing their own automation software. We supply a great Skippy library of all the commands available in the equipment, but if you're developing it while you're taking measurements manually, then it's a very handy feature. We can separate loss values per component carrier, so primary carrier, supplemental carrier 1, 2, 3, etc. We can manipulate how you look at parameters. So there you're looking at multiple carriers that have been folded out to the right there. We can change output levels for each of those individually. So there's just many different ways you can present the data to yourself when you're testing and having to change parameters. Because again, all of this carrier aggregation and multiple channels that you're having to deal with, you have a lot of information you need to change, and you want to change it quickly and not be fumbling around with your GUI. You'll always get on the top right as well the how you're physically connected to the equipment. So there's our millimeter wave up converters, our 28 gig. We've also got 39 and then a multi-wideband that covers all of the millimeter wave frequency ranges. But you'll be able to set your physical ports that you want to use in the front panel, and then you'll always have the GUI there telling you how you're actually supposed to be connected as the software is expecting, or how you've set in the background. So that's for millimeter wave. And then there's a shot there showing you the uplink and downlink for sub-6, because sub-6 comes directly out of our equipment there. So you can always separate the uplink and downlink ports as well. This is in bidirectional, so this is showing, say, a MIMO, or I'm sorry, a single antenna with 4 carrier aggregation. So you have the 4 different carriers there with different uplinks and downlinks going to the same ports. So before I get into the measurements in more detail, I just wanted to take a poll here. I'll hand it back to Rich.
Thanks, Brian. Okay, audience, as I said when we started, we have a poll question for you, so please respond. What technologies are currently integrating in your IoT devices? Is it 3GPP cellular, Wi-Fi, Bluetooth, Zigbee, or something else? None of the above. Brian, we're supposed to chit-chat now while they're putting in their answers.
Hopefully you guys can all hear me good.
Sure can. Loud and clear. Huh. Well, that's an interesting response. Ta-da!
Oh, yeah. So we've got a tie there for cellular and Wi-Fi, Bluetooth not far behind, and then a little bit of Zigbee and some others. So,
what do you think the others are, just out of curiosity? That's a pretty high other number.
Oh, maybe there's closed standard or some of the other narrowband. Yeah, like LoRa or Sigfox or something like that.
Got it. Okay. I will leave the room and hand it back to you, Brian.
Okay, thanks. So thanks, audience. So here's the main RF application. I'll go through this pretty quickly, but I just wanted to give you a really good feel of the measurements. These are a lot of good measurements that we've got. You can see simultaneously, but starting off, you start with the measurement tab there. You get numerical value information. So again, all of this is the same information that you get in the graphical frames there, but just in numerical format. And again, all those arrows you can point down and get more detailed. Say if there's a 2-carrier uplink that you're looking at, you can get that information as well. So occupied bandwidth, this shows 99% of the total RF signal power is displayed in the upper frequency. The frequency within 0.5% of the total power from the upper limit is the measured waveform, and that's determined by the difference in frequency and the measurement uplink that is displayed. That's kind of a common one. Spectrum emission mask, this is important when you're looking at 3GPP type testing. Everybody always wants to be aware if you're below the spectrum mask, you're not radiating power outside of where you should be. But the power at the frequency offset point from the center and the frequency of the RF signal output from the UE is measured. You get uplink carrier aggregation from the primary component carrier, the supplementary carrier. They can be selected and queried too. They're over on the right. And then if you even have a third uplink too, that can be queried as well. Adjacent channel power. This is also a very common measurement. It's the power contained in a specified frequency, channel bandwidth relative to total carrier power. So you want to maintain the call quality by avoiding channel interference. So you want to measure and reduce this amount of adjacent channel power that could be leaking from the transmitter on a mobile phone. So this is a pretty particularly important measurement the carriers always want to know about too. This will tell you if you're having any transmitter design issues, particularly in your low pass filter, but it's not filtering out those low frequency bands that roll off the center carrier. In-band emissions, this is the resource block power spectrum for the data specified by the measurement interval and the measurement offset. So you have markers there that can go into more detail. This is across, looks like 50 resource blocks there. Spectrum flatness for uplink, this is the to calculate the limit lines. The limit lines are automatically added to the in-band emissions trace. Segmentation of the incoming data stream into blocks of so many samples. So in this case, there's 500 or 600 subcarriers. So we compute the squared absolute value of the endpoints across fast Fourier transform of each of the input blocks. Next, the EVM type measurements. So the next few measurements are all kind of related to each other. EVM, is the difference between the ideal spectrum or the ideal received waveform and the measured waveform for allocated resource blocks. In this case, it's 50 resource blocks. So the average EVM is measured at 2 locations in time, high and low, with the high and low locations corresponding to the alignment of the fast Fourier window within the start and the end of the cyclic prefix. And it's presented as a percentage there in root mean square. Phase error. So this will give you information related to EVM, but just looking at phase, looking at your oscillator accuracy or ideal deviation from the ideal signal. It's not looking at the time domain, but the degree of error per symbol. You could also call it jitter in the frequency domain. So here we're looking at the degree of the error and root mean square over the demodulated signals, so it's 0 to 600. Magnitude error, this is the percent of magnitude in root mean square over the demodulated symbols. So in the demodulated reference signal there in a percentage. And then of course constellation, this is a favorite of a lot of RF designers. It's the representation of the signal modulated by digital modulation scheme. In this case, it's a it looks like a 16 QAM signal there, and it'll show you the possible symbols that will be transmitted by the INQ, the amplitude and phase. So you always want to have a nice tight point of INQ there, not splatter all over the place. That'll give you a good indication of your performance of your transmitter. And then finally, bringing all that stuff together, right? It's all going to affect your throughput. So we've got a nice MAC layer throughput. This can be separated out into uplink and downlink. So uplink, you've got supplemental carriers there. So in this case, we've got the primary carrier and then 4 supplemental carriers. So you can get the throughput, MAC layer throughput of each one of those individually plotted out there. And then your uplink as well, so your primary and secondary. You can break those all out too in a SISO mode or a MIMO mode as well. Some additional measurements I thought I'd put in there too that are very helpful is physical uplink shared channel. So looking at the push information that you need to send up, because this is of course the shared information. This is the, in some ways more important than the actual data because it's the control information. The sounding reference signal, so this is always going to be measured by the base station of how your the quality of your conditions are. So it's always going to be looking at the sounding reference signal and seeing if that's as expected, or it will be telling the UE to power up, power down. And then physical random access channel. This is your PRACH. So when you need to do network acquisition, this is a measurement to say how much power you're putting out, because you're going to ramp over time. If you don't get any ACK back from the base station, you're going to keep ramping your power up. So you don't want this power to be too explosive and interfere with other users in the cell. So PRACH, that's a pretty important measurement too when you're looking at IoT devices. And then just skipping down to spectrum monitor. We've got just a general purpose, nice spectrum monitor in there. You can put in markers, you can change the frequency span, just kind of a quick and dirty measurement there. You can change the resolution bandwidth if there's some strange spurs you're seeing in your uplink. Not to be meant for out-of-band emissions testing, although this equipment can do it, but you really need a wider spectrum analyzer, signal analyzer to do those kinds of out-of-band measurements. We can also take a lot of measurements and combine them together too. So we can look at signal quality analysis in different views. So here we can put EVM measurements across symbols, across subcarriers, and do a comparison to see if you're seeing measurements and strange issues going on in different kinds of measurements there. Same thing with all the other measurements that I talked about too, so phase, amplitude, spectrum, and then constellation as well. And a lot of these you can look at simultaneously as well. You can break them out into 4 different plots and look at them simultaneously. Another thing that we can do is we can separate out in subframes the resource blocks and modulation and coding indexes for both uplink and downlink as well. So you can put in different kinds of network conditions. Say you only want to have 2 resource blocks on certain subframes. You want to change around the starting position resource block. You want to have different modulation indexes set for different subframes. We can do that. We can do that while you're in a call too. There's the normal. This is the top one's more of an expanded detail. But the important thing is yeah, we can do this when you're in an established call. There's no need to end the call, change the parameters, bring the call back up, and that's one of the things that the Anritsu equipment, really we pride ourselves on is being able to do a lot of these changes while you're in a call on the fly. We can also change in TDD. You can edit uplink and downlink scheduling This is key to detect different operators and different dynamic network conditions, because you're going to be changing your uplink and downlink slots on the fly. The network is based off of users and conditions in the network. So, if there's a lot of downlink streaming going on, there's going to be more downlink slot numbers. If there's a lot of people uploading video, then there'll be a lot of uplink slots. So you can vary the DCI formats, the time slots, et cetera, in TDD. And again, you can do this on the fly too when you're in a call. This is UE capability information. This has been we've gotten really great feedback from customers when we implemented this. It's evolved over the last several releases, but with carrier aggregation, you're given a lot of bands in combos, and they may not be set properly in the devices. So you don't want to waste your time trying to set combinations that aren't valid in the protocol stack, right? So we've had this since release 11, 3GPP release 11 is this UE capability information. So we've expanded that onto NR now because you've got, ENDC, you've got multiple combinations, and the users love it. Here's channel handover. So again, this is very intuitive. If you're on a channel, you want to change to another channel, do a handover. You simply just go to the channel input area, put in the channel you want to hand over, say OK, boom, you get an RRC reconfiguration message. You're doing a handover immediately while you're in a call, and you can go forward and take measurements on that new channel or band. We don't make you end the call, change the parameters, and then bring the call up. That's the real hassle. Another feature we have is this all screens. You can save the measurements you're taking, save the results. You'll get a parameter summary of what everything was set to, the UE capability. You'll get some layer 3 trace information as well. And that can all be saved on a memory stick or downloaded from the measurement equipment itself. And it's saved in a nice HTML format so you can read it offline, send it to another location if you have multiple development locations around the world. We also have built-in 3GPP TRX test specs built in. We call them single button push. So instead of going through and having to set up multiple parameters to take the 3GPP transmit receive tests, we've got it built in where you can just have what test you want to test. Oh, I want to test maximum output power. You just go into the GUI, select that test, hit run or a single run, and then you'll get your measurement results there. You can also set up multiple tests if you want to do multiple ones as well. A lot easier than old time days back in GSM and CDMA 2000, where you had to set everything up manually. We've had this since LTE days. And there's the single button push. So instead of going and changing parameters there on the left, you just go through, say what tests you want to run, what conditions, what subparameters, and then single button push, and you get pass-fail results for each one of those tests. And then they're showing in the GUI, if there was issues, there'd be a fail, and then what type of measurement. So we have this for LTE, NR, FR1, FR2, standalone, non-standalone as well. Also across technologies too. So for LTE, this is kind of the measurement screen. NR is very similar, and then same thing for CAT-M and narrowband IoT as well. So it's the same look and feel across all of those cellular testing methodologies. It's actually the same underlying hardware. So you buy an Anritsu box for LTE. It'll also test category M, narrowband IoT. It's simply a software upgrade. If you already have equipment in place, you can simply upgrade to IoT. Here's the throughput monitor. So this will give you expected results over there on the left, showing each one of the carriers in expected throughput, total throughput, and then on the little measurement graph there too, you can blow that up and get more detailed. This is for CISO, MIMO as well, so you get different streams across, or data across different MIMO streams. We can go into that level of detail as well. Also for throughput, we've got integrated ping and iPerf, so you can loop the data inside of the internal PC on the equipment and do iPerf pings. So you can just run an iPerf application on your device. A nice quick and dirty way to test upper layer application throughput. Yeah, so we've integrated this in with the GUI. No need to go into DOS, open up another window. We've got it all set there for you. MIMO capability, again, it's just simply going into the GUI, setting up what kind of MIMO you want to do. We support multiple transmit TM modes, TM3 up to TM 10, 11, 12 to test parallel redundant streams of data. What's with the different transmit modes, TM modes are. This is just a propagation matrix for MIMO, 4x4 MIMO there, so you're actually got parallel data going across the different antennas, but that's not always the case. Maybe you want to have different data going across different antennas for greater throughput. Another key concept for testing is dynamic spectrum sharing. So dynamic spectrum sharing, this is going to be rolling out into the operators this year because as we know, there's 4G, there's 5G spectrum, but how are you going to get users to kind of play nice when you're sharing the same spectrum? So it's a way to share that spectrum for 4G and 5G as more 5G devices come on. They need to share that spectrum with the 4G devices. So Anritsu's already integrated this into our measurement, across our measurement software platforms. We've been working with chipset makers on this too. So we can execute rate matching across LTE and NR for uplink and for downlink. The cell-specific resource or cell-specific reference signal, the synchronization signal block. You can't have that stuff colliding. It would just be a disaster trying to get throughput. So you need to carefully segment that out and who's going to transmit when and where and at what time across the spectrum there. And that's what that's showing there at the bottom, is that you can verify different kinds of allocation conditions. So you've got your LTE physical data control channel information, your NR physical data control channel information, your shared channel information split across different frequencies, different times. But with the Anritsu equipment, we've got this auto setting. So instead of playing around with trying to set the parameters yourself there on the left, we've got the ability to auto position the physical data share information, the LTE, the NR side stuff. So the rate matching will be changed, based off of how you've set LTE channel resource block allocations. So there's no need to kind of do this manually. We can do this for you in the software. Another capability that's nice to have for testing is when you've got to do multi-technologies, right? So especially on the cellular side, we've got LTE, WCDMA. We've got all these legacy technologies that in some cases, in some places in the world, they're still used, right? So maybe you have a dual mode phone, or you've got a dual SIM mode phone. You need to be able to test that, or you've got a device that needs to test. You've got to support CAD-M and narrowband IoT. You need to do it simultaneously. That's where this Anritsu parallel phone measurement, or PPM, we call it, comes in. Think of it as two base stations in one. It's an option on the equipment where you can have two separate isolated base stations testing different technologies at the same time. So you could be testing CAD-M and narrowband IT on two different devices or the same device. That's the DSDA, dual SIM, dual active, and then inter-rep measurements too. So say if you want to do reselections, redirections while you're doing data, while you're in idle, different ways to move the device through the network. This is especially key in narrowband IoT and CAD-M, right? There's not a whole lot of mobility built into those technologies. Also with LTE unlicensed and license-assisted access, right? You may be doing LTE in the regular cellular side, and then you may be using the 6 gigahertz, which is the the Wi-Fi kind of band. So you may have a device that's doing multiple technologies at the same time, and then we can do that with the Anritsu equipment. So then bringing it all together, right? It's kind of a phrase I like to use. And, after you've been down in the weeds with all the RF stuff, is we can go in and set up, network conditions that you'll see in the real world. So this is showing, an NR cell, an LTE cell. You can set up different network conditions, what you want to look at, channel, frequency, bandwidth, number of antennas, and then do, mobility testing through the network, adding, removing cells, different channels, etc. And we can do that in the GUI. Here's the FR2 side. So, we've got some great graphs for 2D, 3D. We can rotate, position the view. So you can look at peak beam search, for the FR2 side stuff, looking at radiated power, that sort of thing. This is our Catter chamber. Catter has been a popular chamber architecture for 3GPP and a lot of the OTA testing out there. But it uses a reflector. It's compact antenna test range to shrink down the size that you need. Instead of a far field chamber, you transmit out the test antennas there, kind of in the center of the chamber there. It goes off the reflector and then bounces back to the device under test. That's what you see on the lower right there. And then that's how we get a lot of the measurements out. And then there's our GUI. The nice thing with the Anritsu equipment is it's all integrated. You don't have to worry about the positioner, calibrating for OTA. Our software does all of that for you. You don't have to worry about where the positioner's at. It's not going to go more than 360 degrees and tangle everything up if you've got cables going to your device. The software is very, very cognizant of where it's at and where it's going. And then, of course, there's different kinds of OTA measurement methods too, and you got to consider time because a lot of these tests can take days, hours if you're talking about spurious emissions or out-of-band type measurements. And there's different kinds of steps, right? You take 15-degree steps, 5-degree steps, 30-degree steps, and then there's different kinds of steps. There's constant steps, constant density, so there's different ways, different points that you can look at on a sphere when you put a device inside of that sphere. And then the number of RF converters too. If you have one or two, you're going to be able to do tests much quicker when you're doing 2 converters versus 1. So cellular and Wi-Fi desensitization coexistence measurements. This is a common test when you're having to test a device that has wireless LAN, cellular inside of it. So the Anritsu equipment, we've got software that can control both, the cellular tester, the wireless LAN side, in an OTA type environment, for both Wi-Fi and cellular. And this is getting to be key type RF performance measurement out there because they can overlap sometimes and use the same band when you're talking license-assisted access or LTE unlicensed. So you need to be able to do these measurements, kind of quickly in the same kind of setup and just, you're focusing on Wi-Fi or cellular. Bluetooth and Wi-Fi coexistence, that's another key aspect because they do share the exact same band in the 2.4 gigahertz area. So the Anritsu equipment can do both Wi-Fi and Bluetooth, and we support adaptive frequency hopping. That's the way Bluetooth goes, is it hops around inside the band looking for channels that have interferers. So it'll avoid those. It'll go back and check every once in a while to see if there's still interferers there. But this is your wireless LAN transmitting in the middle and your Bluetooth trying to hop around it. On the wireless LAN side, our GUI is very similar to the cellular side. You get nice plots, information, numerical information as well, change parameters on the left there with pull-down menus. But it's all real-time analysis. That's looking at a nice 1024 QAM constellation plot up there on the top right. In the wireless LAN side, one particular kind of area that has been troublesome is output power. So when you're trying to get a wireless LAN device to connect to an access point or to each other, they'll ratchet their power up. And a lot of times it's not measured until you get an actual call. So we've got this feature where you can do transmit power mode and look at those measurements before you're actually in the connection. So very key measurement. DUT information, very similar to cellular side, where you can look at the capabilities of the wireless LAN device and know what modulation indexes that it supports, what bands that it supports before you start testing it. Because there's nothing like wasting time testing a device that isn't set up the way that you expected it to. We can also do AX testing in PLCP, protocol data unit, so you can move around the resource unit into the different tones. So you've got the different tones there, and whichever one you want to test in, you can move around because it's using OFDMA and AX. So you want to be aware of it. You're not taking up the whole band. And this is the key aspect to why AX is going to be pretty important. Is it's borrowing a lot of the capability that LTE did with OFDMA. Bluetooth side, there's just the Bluetooth packet there, looking at the different preamble, the header information, the payload, the CRC. Bluetooth is a little different than the other technologies. It's controlled by the special interest group, and they kind of set the qualifications that you need to get your device tested. So there's only fixed you put it in a test mode, and there's fixed packets. There are different combinations that you'll have in the payload. There's a picture of the packet there. So you've got the header, the CRC, the payload information. This is in our Bluetooth low energy application. So there's a picture of a Bluetooth low energy under good conditions. This is one where it's got some frequency drift, so you see the payload just off to the low right there. This is with unstable modulation, so you're kind of blasting all over the place there under the payload. This is unstable modulation here, so you see it's jittery all over the place. In Bluetooth 5.1 now, this is the latest, or the latest is 5.2, but that just got approved in January this year. 5.1 offers this angle of arrival, angle of departure capability for location finding devices. So we can measure that now as well. There's been some changes to the PHY layer in 5.1. There's this constant tone extension that's been added on after the cyclic redundancy check. So we've got that ability built into the equipment. And then sensitivity too. So this kind of shares along with cellular as well, that you can do sensitivity testing, packet error rates, frame reception rates, which is the inverse of a packet error rate kind of measurement there. But we've got this all numerical, graphical. Signaling test is the same thing, is a cellular term, but network mode is a wireless LAN term. So they're pretty much the same. And non-signaling and direct mode are the same on cellular and WLAN. What they do is they bypass the protocol stack, so it allows you to jump right into the PHY layer, right, and take PHY layer measurements. And why you want to do this is because you spend a lot of time in signaling mode. You're wasting time doing signaling messages back and forth. So non-signaling will allow you to compact that test time required. And there's different kinds of non-signaling mode too. So there's traditional non-signaling measurements. Now there's sequencing mode measurements. And this can be compacted even in further. Here's some information about a wireless LAN device and you set up your initialization, gut control, measurement, and you go back and forth. Well, with the Anritsu equipment, you can kind of stack this up. If you're careful with how you develop your software, you can shorten your test time down very, very compactly on the left there. So you've got, in this case, one of our equipments that can do 4 simultaneous devices at once. For automated testing, we have Combi Test that can do Bluetooth and wireless LAN simultaneously. It'll cut down your test time if you set the program up just right. It's great for DVT and production testing as well. For cellular side, we've got our ATS software. This is wrapped around 3GPP. You can do all the legacy RF technologies, GSM, WCDMA, LTE, NR. It's a great GUI, lets you go through, select param or test cases you want to run, and you'll get pass-fail measurements. You'll get different kinds of format outputs, so if you want Excel, HTML, PDF, whatever. And this is our product portfolio. So on the top, you've got the cellular equipment, the 8000, which is our main 5G box, and the 8475. That's our network functional tester, network simulator, and our 8821 for RF testing. They all go across various parts of development, evaluation, prototype, and then our 8870 is our non-signaling tester that focuses a lot on production and repair side. And then finally, the conformance side, you've got our ME7800 and our ME7873NR. Those are for conformance, GCF, PTCRB, carrier acceptance type testing. They're pretty much world leaders in this. We've been doing this for quite a long time since our newest generation, the NR. On the bottom there, you've got the connectivity equipment, the 52, the 62, and then the 70 as well that can do short range and cellular equipment at the same time. And then it can also do 5G as well, the 8870. So there's our 8000. This is capable of NR, FR1, FR2. It can do some LTE as well. This is our 8821. We can go up to 8 component carriers, 4x4, so that gets you to 32 spatial streams. That's pretty phenomenal. 3 uplinks, carrier uplinks, and CAD-M, NB-IoT, NB-IoT2, license-assisted access. Our 8475, this is a great GUI, intuitive GUI that'll let you do multiple kinds of IMS testing, VoLTE testing. This is our Bluetooth tester that's been around for a number of years, so worldwide. Our 8862, we've got up to 8X, 802.11ax now, so it's a great GUI. Shows you some screenshots of this, and then our 8870 with different modules that can test multiple technologies simultaneously, because you see it's got 4 different modules and they all act independently of each other. There's 7873 NR or conformance stations, so this does 5G, 4G, 3G RF conformance testing. For GCF, PTCRB, it's got a great GUI tied to it. And this is our simple conformance test system for focusing a lot on CAD-M and NB-IoT2. So just some final thoughts, testing can be done with modern test equipment to simulate the network conditions, the real-world scenarios. If you're not testing this, then what are you doing to test? It's your choice how you want to test your device, getting your device out the door. But in Anritsu, we have the most stable, reliable, repeatable equipment in the test industry. All of our sales associates complete yearly rigorous training to stay up to date on the latest wireless advances. So just get in touch with us and let us, help you out in what you need to do. We have deep local coverage throughout the USA, Canada, the rest of the Americas, and we can discuss, in detail any of the more topics I talked about today. I'll hand it back to you, Rich.
Thank you very much, Brian. That was awesome. And you went through a lot of slides, lots of detail, which is very much appreciated. Okay, this is the time where we answer your questions, and as I said when we started, we will get through as many as we have time for. If we can't answer your question now, somebody from Anritsu will get back to you when we're done, probably via email, but maybe they'll pick up the phone. Okay, let's see. Hopefully, Brian, you had a little drink of water, you read a couple of these questions, and we'll see what happens. Okay. I need to perform carrier acceptance testing as well as conformance testing. Do you do that?
Yeah, so we not only conformance for GCF-PT-CRB, but our equipment is used by the carriers both here in the U.S. and worldwide too. So not just on the protocol side, but the RF side as well. So if you have interest in talking to us about carrier acceptance testing, please get in touch with us.
Okay. How would one run the interference test of two different sets of devices speaking two different protocols, but physically in close proximity of each other? Well, that's a good question.
Yeah,
not that they're not all good questions, but
yeah, so that's a good question. There's different equipment tied to the different types of protocol messages you need to take. So if you have in the case of cellular and Wi-Fi, we have different applications, and if you could physically you could use the same antenna and split it, or you'd have multiple antennas that you can use for communication. But in a signaling kind of mode with those two different technologies, the test equipment's only going to focus on that particular kind of protocol or technology, if you will. The other side will focus on the other side of it. In a non-signaling mode, the equipment knows what to look out for. Essentially, you're just looking at waveforms, and you're analyzing the waveforms. And it'll just pertain to that particular technology.
Okay. Looks like we got time for one more, Brian. Can the Anritsu equipment do CDRX testing? I need to test power and sleep consumption on my device. Yeah,
so DRX testing, we have that ability. You can set the long sleep delays, short sleep delays, wake-up timers, paging information. So if you want to set your device to be on a long DRX and force it to sleep for a long time, we can do that, or short sleeps. That's typically a power consumption or battery type test where you're looking at the test PINX or batteries. But we can set that up in our equipment to emulate the real network conditions, and that's a real key aspect in these IoT devices that need to sleep for or last for 10 years with their battery consumption. So yeah, good question.
Very good. I'm sorry, that's all we have time for. This was good stuff. I know I learned a lot here. If your question did not get answered, someone will get back to you, I promise you. I'd like to thank Brian for a great presentation and Anritsu for sponsoring this event. And of course, we'd never be able to do any of these things without you, the engineer. A final reminder that all Open Systems Media webcasts are copyrighted and may not be recorded without prior permission. Thank you all for attending, and have a great day.